Okay, this is Chapter 9 review. Let's take a look at some of the probabilities that we were dealing with here. First thing is the probability of something happening, and it's simply marked down as count how many successes you can have and count the total different outcomes you can have. What do I mean by that? Well, an example is probably the best way to look at that. Let's talk about what are all the possible outcomes of flipping a coin. Well, you can flip heads or tails. That's the only two possible outcomes. So when I say up here, when you're looking at the formula for calculating the probability, that's what the P stands, of success, you've got to know the total outcomes, and you count those up. And we did that down here with the flipping of a coin as heads or tails. That's two total. And then when you see what's the probability of flipping heads, and that's how you read that, the P, and then what's in the parentheses is what your success criteria is. So the probability of flipping heads is the number of success cases over the number of total outcomes. Well, a success case in this case is heads, so there's only one possible heads success on a flip of one coin. And how many total possible outcomes are there? Our total outcome is 2, because we can have heads or tails. So our probability of flipping heads is 1 over 2. Okay, so heads is our one success, our total is 2, and just knowing our fractions, we know that 1/2 is 50%. So both 1/2 and 50% would be valid ways to answer this problem, or also you could use a decimal 0.5. Okay, so let's do another one just to talk about that again, see a different possibility. What are all the different possibilities of rolling a die? Well, there's 6 sides to a die. I can roll a 1, a 2, a 3, a 4, a 5, or a 6. So there's 6 total outcomes. So we're up here on the total outcome line. There's 6 of them. Okay, well, what if I was asked for the probability of rolling a 4? So the probability of rolling 4 is going to be my successful outcomes. Well, there's only one way to roll a 4, and that's right here. That's one of my possible outcomes, and I know that I have 6 total. So I have 1 over 6, one possibility of rolling a 4, and 6 total possibilities. So there's my 1/4 is the success, and my total is 6. So 1 over 6 is my final answer. Oops, excuse me. Final answer, I need that as a purple. I meant that to be purple there. So 1 over 6 is my final answer when asked what is the probability of rolling a 4 on a standard dice. Same thing again, I'm going to ask what's the probability. This time, the probability of rolling a greater than 4. Well, what are the possibilities of rolling a greater 4? Well, a 5 and a 6 are my possibilities of rolling successfully. Okay, so because if I roll a 4, that's equal to 4, so that's not a possibility of success. There's 2 possibility out of the 6 total. So I write 2 over 6, and I can make that smaller as 1/3. And then if I wanted to, I could make that 33% or 0.3 repeating as a decimal. Okay. And once again, if you're doing it as a fraction, I want it simplified. If you write it as a percent, I will accept, unless it says different on the problem, round it to the nearest percent or 1/10 of a percent. And if you're doing a number 0.33, I need to see the repeating factor somewhere. Okay, all right. So there you go. One of the rules of probabilities is that they always have to add up to 100%. So if I was to ask you, or declare to you that the probability of it raining is 40%, what is the probability of it not raining? Well, it's very simple. Since I know that probabilities have to add up to 100%, I can say that the probability of it not raining right here is equal to 100% minus the probability of raining, which we already know, that's minus 40%. So we have 100% minus 40%, which gives us a 60% chance of it not raining. Okay, and we got that because we know the probability of our two events, raining and not raining, has to add up to 100%, because that's the rule. All probabilities of a single event have to add up to 100%. So when to calculate the other factor in two things, raining or not raining, take 100% minus the raining factor, and that gives you the not raining factor. Now let's try another little thing here. Let's say we're given a table of past events. Here's my outcomes of spinning. I can spin a red. Let's go here, red at 32. Sorry, that's white, so let's undo that. White we'll leave alone at 32. Red gets this off red. 17. Blue, we'll give it a blue. And black we'll circle with black. Okay, so if I was to calculate this, the total number of spins is my total possible outcomes. So if I add the 32, the 17, the 24, and the 7, which I got from right here, if I add those up, it equals 80. So I'm going to mark that down. If you add those up, you get 80. So now, what is the probability of white happening? Well, we know that white was 32 over 80 because of the 32 right here. Okay, I can simplify 32 over 80 into 2 over 5, which is 0.4 or 40%. Once again, any of these answers would be legitimate unless asked for a specific answer. The only thing I would like you to say is if I ask for a fraction answer, I expect the reduced fraction, not the large fraction. Okay, that's only for a final answer. If you want to use this 32 over 80 to do your calculation and come up with 0.4 or 40%, that's fine. Then you wouldn't have to show the 2/5. Okay. Oh, how about a probability of it turning up red? So there's our red probability. Well, we know that red is 17, so we say 17 over our total of 80, which remember we got 80 right there. So there's our total of 80. You use your calculator to get that. You get 0.125. Let's do that in red. 0.125 or 21.25%. And then we've got the probability of blue. Probability of blue is 24. Got that from up above in our chart, our table, out of 80. We can just do that all in blue, it doesn't hurt. Out of 80, which gives us 3 out of 10, which is 30%, or 0.3 or 30%. And finally, the probability of black, we're gonna use this. Probability of black, well, we know it's 7 out of our total of 80. So 0.0875, which is 8.75%. So when we add all those probabilities up, if we were to use the fractions, we would have the first one, the probability of white using a fraction, plus the probability of red using a fraction, probability of blue using a fraction, and the probability of black using a fraction. That adds up to 80 over 80. 80 over 80 is just 1, and we all know that the number 1 is the same as 100%. And this would all work out even if I did different numbers. Let's say I use the decimals, 0.4 for white, 0.2125 for red, 0.3 for probability of blue, and 0.0875 for the probability of black. Those all add up to 1, which is also 100%, which it makes sense. We should get the same answer in all 3 of these lines. And finally, let's use red here. If I was just adding up the percents, there's 40% plus 21.5% plus 30% plus 8.75 gives me 100%. And we did end up with the same answer in all 3 places. So, well, let's try it for real. If I was given this spinner, it could spin 1, 2, 2, 3, 4, 5, or 6. And I did a bunch of spins, and I counted each time it landed on the 1, the 2, the 3, 4, the 5, and the 6. Well, I'd say, and then I was asked, what is the probability of spinning a 5? Well, I look at that and I see there's the 5, and there's the number of times the 5 occurred, okay? So I just have to say, the number of times the 5 occurred is going to be the number of successes I had. So that's 17. And on the bottom, I need to know the total. Well, what is the total amount of spins? Well, I just add these numbers up together in the spin row. And I can see that in doing mental math. I can say 10, 30, 40, 50, 60, 70, plus 7, 2, 19, 20, 28, 35, 40. And that's 110. Actually, that's 100. I added somewhere. 10, 20, 30, 40, 50, 60, 70. Okay. I must have made a mistake somewhere. That should have added up to 100, but 110. Yep. 70, 79, 80, 88, 95. This is 30. All right, so that's 100. There we go. My mental math was a little off there, but 70 plus 30 is 100, and that's the number that goes on the bottom, so I write 100 on the bottom. So 17 out of 100 could be a good answer, or I could write 0.17, or I could write 17%. Okay. When finding the probability, new item here, when finding the probability of multiple outcomes in one event, add the probabilities of each event together. So, if you're given a problem where they ask you for the probability of rolling a die and getting a 4 or getting an odd number, well, what you want to do is say, what's the probability of rolling a 4, and add to it the probability of rolling an odd number. So the probability of rolling a 4, we've calculated that up above, is 1 out of 6, because the probability of rolling a single number on our dice roll is always 1 out of 6. Well, odd numbers, there are 3 odd numbers in 1, 2, 3, 4, 5, and 6. There's the 1, the 3, and the 5. There's 6 total possibilities in rolling one. So 3 out of 6, we add those together, we get 4 over 6. We can reduce that to 2/3. We could write it as 0.6667, or 0.66 repeating, or we can write it as 67%, or 66.7%, depending on where you want to stop your rounding. Okay, so let's do our one on our own. What's the probability of rolling a 6 or a less than 3? Well, it asks us to do formula using probability. Write the formula using probability notation. So we're going to say the probability of rolling a 6 is written like that. Plus, because we're going to add these two together, the probability of rolling a less than 3. Okay? And now we can just say down here, it's asked you to do the fractions. Right here, it's saying let's do the fractions. We'll do that. We know that probability of rolling a single number of the dice is always 1 over 6. And we're going to add it. The probability of less than 3, well, that's really 1 and 2, right? So that's 2 out of 6. So there's 2 possibilities. So we write that here, 2 out of 6. We add those together, we get 3 out of 6. We know that's 1/2. That could be our answer, or we could go ahead and write and say 0.5, or we could write and say 50%. So any one of those answers would be valid. Now, just to tell you, this is going to be requirements at least somewhere on the test. All right, now let's do a new concept, talking about a code that contains 4 letters. This is called the counting principle. We're going to ask how to find the possible number of codes there are, and in the code that contains 4 letters. Well, what you do is you just take the number of options in each step, in each letter, and multiply it by the number of letters you have. So there's 26 possible options in the first letter, times 26 more options in the second letter, times 26 more in the third, times 26 more in the fourth. So a simple calculation is take how many different things there are for, in this case, letters. There's 26 possible letters in the alphabet. Multiply them together for each one of the 4 spots where you can have a letter, and there's 450,000 plus codes in a 4-letter code. All right, now let's try another version of this. If a room has 6 doors, how many ways can you enter and then leave the room? Okay, well, to calculate that, you say, how many ways can I enter a room that has 6 doors? Well, there's only 6 possible ways to enter a room that has 6 doors. How many ways then can I leave the room? Well, there's only 6 possible ways. I can use any one of those same 6 doors I just walked in. And so there are 36 total when I multiply those together. Now, if they had told me, take this same problem and say you can't leave by the same door you came in, now how many possibilities are? Well, I can still have the same number of options to enter the room, 6, but now one of those 6 doors is closed off to me. The door I just walked in, I can't use again. I can't turn around and go right back out it. So once I'm in the room, there's only 5 options to get out of the room. So the total now becomes 36 times 5. Now let's talk about when you're choosing some subset of things from a bigger set of things, and if order matters or order doesn't matter. What's that called? Well, it's called either doing a permutation or a combination, and we see they're written fancily as NPR, where N is the number of total numbers of things you have in your bag to choose from, and R is the number of things you're going to choose. And if it's C, it's the same thing, number of items you can choose from, and R is the number of items you're going to choose. In a permutation, the order matters. If I have A and B, it is not the same as B then A. So this is the formula there, n factorial, and if you remember that n factorial, for example, if it was 5 factorial, is equal, just take the first number and multiply it going down by 1 until you get to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1. 4 factorial will be starting at 4, 4 times 3 times 2 times 1. A million factorial would be a million times 999,999 times 999,998, and so on all the way down to 1. Okay, now back up here to the combination. This is the order doesn't matter. Over here, in the permutation, AB is not the same as BA. Over here in the combination, the AB is the same as BA. We don't care if it's AB or BA. We're going to count that as one possible combination. Whereas on the left, with a permutation, AB is considered completely different than BA. And how are these two? What kind of English situation and wording do you need to look at? Well, I always look at it because of the word combo here, combination. Think about it as ordering a combo pizza. If I order a pizza with pepperoni and onion, I consider that the same as ordering the pizza with onion and pepperoni. So the fact that I have pepperoni and onion is what I'm worried about, not the fact that pepperoni came first and onion came second. Okay? If I'm over here in the permutation, I remember that perspiring runners care about first and second. Okay? So if they care about first and second, that we know that if Mary comes in first and John comes in second, that's a total different scenario than if John comes in first and Mary comes in second. So just remember, combo pizza is like a combination. Pepperoni and onion is the same as onion and pepperoni, and permutation is the same as perspiring runners, where the place coming in first and second does matter. All right, now an example to try to explain this, I'm going to show you the exact same problem. You have 5 plants. You need to put them in order on a shelf. And the shelf only fits 3, and on the left-hand side, the order matters. On the right-hand side, we have the exact same scenario, 5 plants to put on a shelf that only fits 3, but on this side, the order does not matter, okay? So, for example, on the left-hand side, if I had a cactus, then let's say a tree, and then a flower, that's totally different than if I had a tree, then a cactus, then a flower. Those are 2 separate things. But over here, cactus, tree, flower are the same as flower, tree, cactus. It doesn't matter as long as it's the same 3 items. We don't care what order it is. Over here, these 2 are different. Over here, these 2 things are the same. Okay, so what's different in our calculation? As you see in our formula, the only difference between the 2 is this R factorial on the bottom of our formula. So, in our permutation in our trees, we have 5p3, which means I have 5 factorial on the top, and then 5 minus 3 factorial on the bottom. That's 5 factorial over 2 factorial. Writing that all out the longhand, it's 5 times 4 times 3 times 2 times 1 divided by 2 times 1. I take the 2 times 1 and cancel it on both sides, top and bottom. I'm left with the simple 5 times 4 times 3, which tells me that I have 60 ways to order those plants, those 5 different plants in a shelf that only fits 3, and where order matters. Now on the right-hand side, we're going to do the same thing, but this time, 5C3, the C is different than the P. That tells us that the order doesn't matter, so we still have the same 5 factorial on the top. We have the same 5 minus 3 factorial. What's new now is we have the 3 factorial, which comes from this number right here. Okay, so expanding that all out, we end up with 5 factorial divided by 3 factorial times 2 factorial. There's our 5 factorial expanded out. There's our 3 factorial expanded out. There's our 2 factorial expanded out. First thing I'm going to do is cancel out the 3, 2, 1 and the 3, 2, 1. That leaves me with 5 factorial on the top and 2 times 1, or 5 times 4 on the top and 2 times 1 on the bottom. 5 times 4 is 20, divided by 2. And there are 10 ways to make combinations of my 5 plants and put 3 of them on the shelf. So that's the difference between a combination and a permutation. There will be at least 1 problem for each. All right, new concept. When multiple probabilities occur in sequence, multiply them. So, example, what's the probability of flipping heads and then rolling a 6 on a die? Well, what you do is you take the probability of heads times the probability of rolling the 6. Well, we know that the probability of flipping a coin is heads or tails, and it's 50-50, or 1/2 probability of heads, and 1/6 probability of rolling a number on the dice, a specific number. And if you remember how to multiply fractions, you multiply top numbers on the top and the bottom numbers on the bottom, so we get 1/12. So basically, it's 1/12 probability that you can flip a coin and then roll a dice on a 6. So let's take a look at another example. If we're given a jar with 3 red marbles and 4 black marbles, let's take a look at it. We're going to look at it 2 different ways. If I replace, excuse me, if I draw the first marble and replace it, or if I draw the first marble and do not replace it. Let's talk about replacing it first. If I'm going to replace it, and I have my probability of drawing red, I'm going to get probability of 3/7, okay? Because there's 3 red and 4 black, so there's a 7 total. My probability of black is 4/7, because there's 4 black marbles, okay? And now we're asked what's the probability of drawing a red, then black, with replacement. So that means that the probability of drawing a red, which was 3/7, times the probability of drawing a black, which was 4/7, gives us 12 over 49, which is, 24.5%. Excuse me. Now let's do that same problem, but this time we're not going to replace it. So we have the probability of red. That's still going to be 3 out of 7. Same scenario we started with in the first example. But now this time we're not replacing that marble. So there's only going to be 6 marbles left in our jar, but 4 of them are still going to be black. So the probability of drawing black in this scenario is that 4 over 6 instead of 4 over 7 that we saw in the first time. So we take that 3 over 7 probability of red times the probability of then drawing black, and we end up with 12 over 42, and we get 28, a little about 28.5% or 28.6% chance of doing that. And why is this number on the bottom? Why is this second number bigger than the first number? Well, if you think about it right here, we have, since we didn't replace the red marble into the sack, there's still the 4 black marbles, but now there's not a 7 total, but a 6 total, so there's a slightly better chance of getting that black marble on that second drawing. So we would expect the replacement would have a lesser probability than if we do not replace that first red marble. All right, let's try it. A die is rolled 3 times. What is the probability of rolling a 6, and then another 6, and then a 1? Well, using our probability formula, and we know we have to multiply those, we say the probability of rolling a 6 times the probability of rolling another 6 times the probability of rolling a 1. Well, we've done this many times today. 1/6, 1/6, and 1/6. And make sure you're multiplying them, not adding them, because the question is asking it, what is the probability of rolling a 6, then a 6, then a 1? It's not saying what's the probability of rolling a 6, then do another whole probability of rolling another 6, then another whole probability of rolling a 1. This time it's a probability of rolling 3 times in a row, getting a 6, then a 6, then a 1. And you multiply those out, and you end up with 1 over 216. All right, let's do another example. 2 cards are drawn at random from a standard deck. What is the probability of drawing red, then black? Well, if I was to write this out, I'd say the probability of red times the probability of black. Okay, so we're going to assume that you pull the deck and there's no replacement. Because normally when you draw a deck from a card, then you don't put it back in the card deck, you don't reshuffle, you just draw the second card. So that's what we're going to assume is happening here. So the probability of drawing a red card, well, if you know a standard deck of cards, there are 26 red cards and 52 total cards. 26 red and 26 black. So drawing a red. Now the second draw of drawing black, there's going to be 26 blacks, but there's only going to be 51 total cards in because we didn't replace the first card we drew. So we're going to have slightly better odds or probability. And I'm going to have to do this on my calculator here. 26 times 26 is 676. And over 52 times 51 equals 2652. And I'm just going to divide those numbers on my calculator. 676 divided by 2652. That leaves me with 0.25, and I'm going to round it up to 255, or approximately equal, that's approximately there, 25.5%. Okay, and finally, the last lesson we had in the class was, what's the difference between probability and odds? Remember, probability is equal to success over total, whereas odds is successes divided by failures. So if we had the problem of a number from 0 to, or 1 to 9 is randomly selected, what are the odds of selecting an even number? Well, we have to calculate the number of successes. Well, if 1 through 9 successes of an even number are 2, 4, 6, and 8, so there's 4 of them, and failures are 1, 3, 5, 7, and 9, so there's 5 of them. So the odds are 4 to 5, and you can call that the odds for that happening. If I was asking you to do the odds against something, and you already know the odds of it for, all you do is rewrite it, write it in the opposite way. Flip those two around. The odds for something happening are 4 to 5. The odds against that very same thing happen are 5 to 4. Doesn't matter what the number is, you just flip it around to be for or against. So let's not look at this. This was a typo. And let's go down here. Now what are we gonna, let's use it. I did correct this, sorry, excuse me. So now we have the odds for and against. It's asking us now for, here was the typo. I want the odds for and against selecting an even number. No, I want the probability. And remember, probability is success over total. So the probability of the odd or even number happening is going to be 4. Remember, we figured that out right here, that an even number happening is 4. But what's my total now? My total is, 4 and 5 is 9. So that's the probability, 4 over 9. Where the odds were 4 to 5, the probability is 4 over 9 over the total. Okay? So that would be my probability for that happening. My probability against that happening are going to be the failures over the total instead of the successes over the total. Okay? So, very simply, when you do probability, you got to watch what you're doing versus odds. It's still basically the same 3 numbers. So once you know odds or you know probability, you can figure out the other one. If you know probability, you can figure out the odds. If you know the odds, you can figure out the probability. It's just a matter of knowing these 2 formulas, successes over failures or successes over total. And that is the review.